Okay, this is an example problem for Physics 1000, Auburn University, summer 2013. This is a problem we worked out in class. It's a kinematic problem, and if you remember, the criteria for for working a problem in with a kinematic equation is that you don't care about the forces and that the acceleration is constant. So in this case, we have both of those situations. So we can feel free to use a kinematic equation. So the problem as stated was that a ball rolls down a hill. It starts from rest, and at 7 seconds after we let the ball go, we measure its velocity and find that it's 25 meters per second, and we're being asked to find the acceleration. So the first thing I've done is, the first thing you should do when you try to solve these problems is draw a picture. I put a ball here to tell myself that that's where it started, and I put a ball here to tell myself that that's where it ended. So I know in my own mind that the ball moves. It's the same ball. I just wrote it like that to make it clear in my mind. And so now I'm going to label everything that I can label on this. I know that at the first position I'm going to have some sort of initial time, basically what the stopwatch reads when I start it. And I'm going to have an initial position where the ball starts. I'm going to have an initial velocity, how fast the ball is moving when I start my stopwatch. And I'm going to have an acceleration here. And when when I measure the ball 7 seconds later, I'm going to have much of the same situation, except these are all going to be final. Final time, final velocity, final position, and final acceleration. Now, I've gone ahead and subscripted the acceleration with an I and an F. But really, if you think about it, I don't need to do that. I've drawn it here just to be perfectly clear. But remember, what we've said is the acceleration is constant. So if there's no need to, if I can find my eraser, if there's no need to tell me that it's initial or final, we can just call it A. So we have an A at the beginning and an A at the ending, and we know that they're the same A. Okay, so basically this is all the information I can glean from the problem. So now what I'm going to do is I'm going to make a chart, which I've already done. I'm going to go read through the problem again and see what I know and what I don't know. And what I've come up with is that I was given the initial velocity because the problem stated that we started from rest. I'm given the final velocity because the problem stated that it was 25 meters per second. And we said that we measured it after 7 seconds, which is my time. And we said that my x initial was 0 meters because we set our 0 position. And you might also ask, why don't you have your initial time and your final time on here? And as we stated in class, you always have the power to start your stopwatch at t equals to 0. So if your initial time is 0 and your final time is something else, if you remember, your delta t is just going to be whatever your final time was, because you'll just be subtracting 0. And this is going to be the same thing generally in your x position, although in this case it's a little different because we don't know our final x position. So those are my knowns or my givens, and I've listed my unknowns. I don't know what the acceleration is, and I don't know what the final position is. So now what I have to do is figure out what equation to use. So I go to my toolbox, which I've written down over here, and I look at these equations and I ask myself, what do I know, and what can I find out? So let's look at this equation first. This equation is an equation for, it gives you a final position when you're given all this other information. Of course, if you're given a final position, you need something else in this equation, you can always rearrange it. But in this case, I don't think we even need to go any farther, because do we know our final position? No. And do we even care about our final position? The question, remember, asked us for the final velocity. So there's a bunch of stuff in this second equation that we just don't need. So I think right off the bat we can go ahead and say, nope, not using that one. So let's look at this equation here and see if it has everything we need. What we're being asked to find is the acceleration, and sure enough, the acceleration is the term here. What we know the initial position, because we said it was 0. We know the final position. I'm sorry, not position. We know the initial velocity and the final velocity, because those were given. And we were also given the time. So look at that. We know everything in this equation except for the acceleration, which is what we're trying to find. So I think we have a winner here. I think we're going to go with this equation, the first one, the final velocity equals the initial velocity plus the acceleration times the time. So I'll go back over here, and now I'm just going to rewrite that equation in my equation column. Final velocity equals initial velocity plus acceleration times time. So now, let me go ahead and sort of block this off. Now I'm actually going to solve the problem. I've got my picture, I've got my table, I've got my equation selected out. Basically at this point the physics is over. I've completely characterized the problem and now it's just algebra. So I'm going to come down below and solve it. So V final equals V initial plus AT. And remember what we said in class, we don't plug in numbers yet. But if we have any zeros, now is a fantastic time to plug them in, and we sure do. Look at this, the V initial right here is listed as 0, so this just goes away. It becomes a 0. And so underneath this equation I can rewrite the final velocity equals the acceleration times the time. And remember, what I'm being asked to find here is not the final velocity. I'm being asked to find the acceleration, so I need to rearrange this equation, which I can do just by dividing both sides through by t. And I'm going to go ahead and list my a on the left side, just because I like to do that. So dividing the VF by t, this is what we get. And so what we have here is our acceleration by itself, and the rest of the terms on the other side of the equation. So basically we solved the equation. So now is the perfect time to plug in some numbers. And what you do, if you get that, you get a is equal to 25 meters per second over 7 seconds. And this would be the time to plug this into your calculator, or you can leave it as 25 over 7. That won't reduce any farther, and I'm perfectly fine with that. Or you can plug it into your calculator and get a decimal number. It doesn't matter to me. But like we said in class, a good check for yourself, and this is not required for you to show this, but we know that the units of acceleration are meters per second squared. So I will not count off at all if at this point you go right here and say, well, we know that that's 25 over 7 meters per second squared. But to check yourself, check and make sure that your units work out algebraically. In this case, what we have here is 25 meters per second over 7 seconds. So let's just work with the units and make sure that what we get is a meter per second squared. So I'm going to move to a new slide because this is getting a little crowded. I'll just do it here. So we have meters per second over seconds. And we know that this is supposed to be meters per second squared. So algebraically, some of you can see this, some of you might need to take the step, which is totally fine. To work out this side of the equation, you can take the denominator, meters per second, and separate this, multiply it by 1. I'm sorry, you take the numerator, meters per second, and multiply it by 1 over the denominator, like this. And then you come up with meters per second squared, just like what we're supposed to have. So that works out. So the key is deciding which equation you need to use based on what you have and what you need to find.